Heat exchangers are devices where we have two fluids. Usually one of the fluids is coming in at a low temperature and the other one is coming in at a high temperature. Of course, like the name implies, the interaction between these two fluids allows heat to flow from one fluid to the other. The schematic for these heat exchangers can be as simple as a 2D enclosure where m.1 at T1 comes into the box and m.2 at T2 comes out of the box, and then m.3 enters our control volume flowing through a duct that passes through it and exits as m.4 at T4. Of course, because this is a steady state device, mass flow rate 1 equals mass flow rate 2 and 3 equals 4. With heat exchangers, we usually ignore the changes in kinetic energy and potential energy. The casing of these heat exchangers is very well insulated, meaning they are adiabatic, which is the definition of no heat transfer. Now, of course, no heat transfer refers to coming in or out of the heat exchanger itself. There is no heat coming in or out of the control volume, but of course there's going to be a heat transfer from the hotter fluid to the colder fluid. And as for work, no work is done on or extracted from a heat exchanger. With all of these conditions and assumptions, our energy conservation equation results in that the sum of mass flow rates coming in times their incoming enthalpies is equal to the sum of the mass flow rates coming out times their exiting enthalpies. If we have two fluids, we know that M1 and M2 are the same and M3 and M4 are the same. This expression results in M.1 times H1 minus H2 equal to M.3 times H4 minus H3. This makes a lot of sense because if there is no work or heat coming in or out of the box, it means that the heat lost from our fluid is the same as the heat gained from the other fluid. We can obtain this single expression from a control volume that encompasses the entire heat exchanger, or we could draw two control volumes, one for fluid 1 and one for fluid 2. Since for each of them the change of enthalpy is the heat being transferred, but the heat that comes out of one is equal to the heat coming into the other, the resulting expression would be the exact same. And that's heat exchangers. The last device we're going to have an overview of is the mixing chamber. Remember that if you want to learn about pipe flow, nozzles, diffusers, and throttling devices, as well as turbines, compressors, and pumps, the two previous lecture videos cover these topics. The links to those videos are in the description of this one. The difference between the mixing chamber and the heat exchanger is that in mixing chambers, the two fluids don't remain separate after exiting the device. In a mixing chamber, both fluids combine or mix inside of it. We can draw it as a box with two inlets and just the one outlet, where m.3 leaving at T3 is the sum of m.1 and m.2. The schematic itself can be a little bit more refined if you want to. Just like with heat exchangers, we ignore heat and work as we do for changes in kinetic energy and potential energy. The energy conservation equation reduces to m1h1 plus m2h2 equal to m3h3. And of course, if there's more inlets, then you add them at the left-hand side. Sometimes you have two or more outlets, but then the system schematic of what inlets are being mixed needs to be very clear. Let's look at a not-so-simple heat exchanger example where we use what we just learned, and if you want to check out a mixing chamber example or other more complex examples on this topic, make sure to check out the links in the description below. Air is flowing through a heat exchanger so that it cools down from 780 Kelvin to 340 Kelvin, while the pressure remains the same at 1 megapascal. The heat exchanger uses water as the coolant, which enters at 10 degrees Celsius and leaves as a saturated vapor at 100 kilopascals. What is the ratio of the flow rates m.water over m.air? Additionally, if the mass flow rate of air is 4 kilograms per second, what would the minimum mass flow rate of water need to be to prevent any water vapor from forming? And what is the heat transfer to the water? Remember to pause here and try to solve this problem yourself before watching the solution. From what we learned today, our energy conservation equation for the heat exchanger was reduced to the change in enthalpy of one fluid in one direction is equal to the change in enthalpy of the other fluid in the opposite direction. Solving for the ratio of the flow rates we need, we find that it's just H1 minus H2 over H4 minus H3. This expression could very well be H2 minus H1 over H3 minus H4. Just make sure that you're moving the negative signs correctly when solving for the variable of interest, and that you check that the expression that you obtain makes sense as well. Here, if we look at either of these expressions, we would expect that because the water is heating up while cooling the air, the exit enthalpy of water H4 is greater than the inlet enthalpy of water H3. And because the air is cooling, its exit enthalpy H2 is lower than its inlet enthalpy H1. So in the expression to the right, we have a negative value over a negative value, and in the first expression, we have a positive value over a positive value, which both result in a positive ratio. This should in fact be the case because a ratio between positive flow rates should be positive. If the ratio itself was negative, it means that one of the flow rates is negative, and that doesn't make sense. So how can we find these four enthalpy values? Well, if you remember from our specific heats 12-minute lecture video, linked below, the enthalpy of an ideal gas is a function of temperature only. So for the air, we have the options we discussed in that previous lecture. Using Cp from cold air, using an average Cp between T1 and T2, using the polynomial fit for Cp and integrating, or of course, the one we concluded was the most accurate and quicker to use, the property tables. So if we go to our property tables, in this case the ideal gas properties of air, we can look up the enthalpy for the inlet temperature, 780 Kelvin, and the enthalpy for the exit temperature, 340 Kelvin. Now for water at 100 kilopascals, which is very close to atmospheric pressure, we know that water at 10 degrees Celsius is a compressed liquid. So for the water inlet, state 3, we could go to compressed liquid tables, but if you remember what we learned in the compressed liquid 6-minute lecture video, linked below, we concluded that we can approximate compressed properties as the saturated liquid properties. And in this case, we have to use this approximation since the compressed liquid tables won't have such a low pressure value anyways. Check that video lecture again if you don't remember this. So to find H3, we go to the saturated water tables, the temperature version, and write down the saturated liquid enthalpy HF for 10 degrees Celsius as the value for H3. Brief parenthesis here, remember you can get a slightly more accurate value here using what we learned in the specific heat and energy changes for incompressible fluids 11-minute lecture video. Link below if you don't know where this is coming from. And since state 4, the outlet of water is at a saturated vapor phase, we go to the saturated water tables, this time the pressure version, since what we know about the exit is that the water vapor is at 100 kilopascals, and write down the saturated vapor enthalpy Hg for 100 kilopascals as the value for H4. And with this, we can go back to the mass flow rate expression we found earlier and substitute all four enthalpy values. This results in a mass flow rate ratio of 0.1747. Alright, so now for the second part of the question. If we want the water at the exit to not have any vapor in it, it means that state 4 needs to be here at a saturated liquid state. The values for H1 and H2 have not changed because that's the air, and even H3 hasn't changed either because that's our water at 10 degrees Celsius. The only difference here is that H4 is no longer the enthalpy for saturated vapor Hg, but the enthalpy for a saturated liquid, which is the limit for no vapor at all at 100 kilopascals. We get this from the saturated mixture tables. Solving for the mass flow rate of water, we substitute all values and we get that we need 4.9 kilograms per second of water, so that after cooling down the air and therefore gaining heat from it, the water is still in a liquid phase. And what about the heat exchanged? Well, remember that if we split the system into two control volumes, one for the water and one for the air, the heat coming out of the air is the same as the heat coming into the water. So we can choose either of them. We substitute the values for either or both and find that the heat transfer is 1840 kilowatts. If you want to check out mixing chamber examples, as well as other heat exchanger examples, or just the other lectures of the thermo course or even other engineering courses, make sure to check out the links found in the description of this video. Thanks for watching.